Okay, let's go ahead and begin. Hello, everyone. My name is Emily Kloss, and I'm a communications coordinator at the National Renewable Energy Laboratory and support the Global Power Systems Transformation Consortium, also known as G-PST. Today's webinar is presented by G-PST's Pillar 5 and LF Energy and is titled Open Source Power Systems Analysis Packages, Cross-Package Coordination for System Planning. Now, before I pass it over to our technical presenters today, I did want to go over a few housekeeping items with you all. The first is that this webinar is being recorded and it will be shared with attendees in the days following the events. As an attendee, you can expect to receive a follow-up email with the webinar recording and any resources and materials shared during the event. You will be automatically muted upon joining and throughout the webinar. If you would like to share introductions, add comments, or anything else, we encourage you to please use the chat feature. If you would like to ask questions to our technical presenters at any time, you can do so by using the Q&A function on your toolbar. And if you have any trouble locating this function, please just send me a message. It's at the bottom of your screen. We do have time carved out at the end of the webinar for our technical presenters to answer your questions, but please feel free to ask questions at any point during the session, and we'll be sure to answer them at the end of the event. If you're having technical issues, please use the chat feature to message me, Emily Kloss, and I will be happy to help you. And lastly, you can adjust your audio through the audio settings. If you're having issues, you can also dial in and listen by phone, and all of those details can be found in your registration confirmation email. And we do have a short survey that will launch at the end of the session, and we do encourage you to please participate in the survey. Your responses really help us improve these events, tailor content and topics, and also, most importantly, gain support to host future free events for you all. And with that, I will now hand it over to Juha Kiviloma, who is the G-PST Pillar 5 lead, who will kick off today's webinar.
Thank you, Emily. So, my name is Juha Kiviloma from VTT Technical Research Center of Finland, and an energy system model developer, and also involved in the Pillar 5. The intro will be done together with Benoît from RTE, and today we will have a G-PST presentation, Hannele Holtinen, Clayton, Barrows, and myself from Pillar 5, and from LF Energy, Julie Goodman and Benoît Jeanson, and from RTE. And then the actual presenters will be Maximilian Bartzen, presenting PIPSA. He's from University of Edinburgh. Panda Power will be presented by Roman Bulgarin from Fraunhofer IEE. Then we have Possible presented by Nicolas Aumont from Artelis. And then Powersimulations.jl will be presented by Clayton, Barrows and Deepak Krishnamurthy from NREL. Next slide, please. So here are the kind of leading members of the Global Power System Consortium. Next slide. And then just very shortly, I know many of you have seen this already before. So the G-PST is formed by 5 pillars. The first one does research to enable inverter-based power systems. The second one scales these to get best practices to the transmission system operators across the world. The third one helps to develop the workforce needed to implement all of this everywhere. And then fourth one is about adopting technologies in different localities, helping to build standards and such things. And the fifth pillar, our pillar, is about open sourcing data and tools. All right, then I'll give over to Benoît, who will introduce LF Energy.
Hello, everybody. So my name is Benoît Jeanson. I work for RTE, and RTE is actually a member of the Linux Foundation Energy, and that's why I'm introducing Linux Foundation Energy today. The goal of the Linux Foundation Energy is to provide a 21st century plan of action to decarbonization through open source, open frameworks, reference architectures, and the support ecosystem of complementary projects. And as you know, we are facing huge transition regarding the fact of global warming, and we need to have an energy transition. And we think and we believe that open source is an enabler to grow the ecosystem, the software ecosystem that is needed to face this, to meet this challenge of the energy transition. So that's why the Linux Foundation was launched, and it was launched a few years ago. And next slide, please. And as you can see, it's a really growing ecosystem of software now that are available in open source. And so you have many projects, and at the beginning it was a sparse project, but now they're connected more and more together, and we start to have a really consistent ecosystem of open source software that are to be used for utilities, TSO, DSO, aggregators, but other actors. And we are dealing with many things such as forecasting, simulation, electric vehicle, data transmission, that from the substation to the control room. So we are addressing all the business requirements of the utilities to support their business activities. Next slide. So the Linux Foundation Energy is now growing, and so that's just a new update of the slide, because very recently Microsoft joined as a strategic member. So we have Alliander, Google, Microsoft, and RTE that are strategic members, and then you have a bunch of general members and associate members, and so that's also showing a lot of interest. And so Linux Foundation Energy is having a lot of interest, and we are very happy to see that there are more and more companies that are joining and putting their force together to change the world. Thank you.
And I'm Clayton Barrows, and I'll give a little introduction to the workflows and the problems that we're going to be presenting today. Next slide. Yeah, so the general agenda of the technical content, we'll just do a quick introduction, and then we'll step through demonstrations and some analysis from each of the tools mentioned, and then we'll conclude with some quick outcomes and lessons that we've learned through this coordination process. Next. Again, the contributors span membership from G-PST, and then from the tools themselves, PIPESA, Panda Power, Possible, and Power Simulations. And in addition to the folks that are actually presenting today, there are most of the other folks that have contributed, either be helping with some background development or analysis, are also listed on this slide. So there's some additional students and colleagues that we've all gotten some help from on this process. Next slide. So we will again focus on the data, that an open data set that's available called the RTS GMLC, which is an extension from the RTS 96. There's some publications and data sets available and data available to describe this test network that was originally built up by an IEEE task force. And we've chose this because it's reasonably small with 73 buses and easy enough to work with. It also has enough suitable data that we can do some somewhat interesting planning case studies. And so we will start with this RTS GMLC network and do a variety of different modeling activities on that network. Next slide. So the previous workflow, or the previous event that we presented, we used the RTS GMLC and another data set, and we focused on solving the exact same problem across a number of different tools and comparing the workflows and the performance of each of those tools. In this event, we're focusing on using a common data set and doing different modeling activities with that data set, and in some cases passing data in between those modeling activities to make a common coordinated workflow. And so we're starting with the RTS GMLC base network, and then in principle, we're expanding that network or modifying that network through various analysis with or calculations with PIPSA, and then using the results of the PIPSA model results to instantiate various operational analysis and calculations and modeling with Panda Power Possible and power simulations. And so that's generally the workflow. The idea here is that we show some of the focuses of the different tools and the ability to translate data that may not be in an extremely standard format and be able to pass the results in between the two different tools. Next slide. Ultimately, we're hoping that we're able to demonstrate the value of some of the open source capabilities and the capabilities that are enabled in the open source community. But I think more important than that, showing that coordination is possible across these tools, and sometimes the fact that the tools themselves are open and have openly accessible data models and things like that help make it possible to do the coordination across multiple tools. And then we've even, in this process itself, we've started to standardize some data specifications and build some additional interoperability. I think that that's one of the main conclusions that we'll discuss at the end as well, that we need to do more of that. Next slide. With that, I'll hand it to Max.
All right. Can everyone hear me well?
Yes.
Okay, great. Yeah, my name is Max, and basically I'm just introducing myself quickly and who I'm working with. So basically I'm a PhD student at the University of Edinburgh, and I'm co-steering the PIPSA Meets Earth initiative, which we founded actually just last year. And yeah, we actually have at the moment around 10 full-time developers, so not just users, but developers. And yeah, just increasing. And what motivates us working together is, as Benoît said, that we want to solve the big problems faster. And we really believe that we can do it in that way. And actually we're doing it. So PIPSA, yeah, PIPSA is this model, it's a model framework, so it can formulate a power system problem or energy system problem, and you can find optimizations, like a optimized result. It was actually developed mainly through Tom Brown and some colleagues from him. And yes, since then, over the last 5 years, it quite evolved to a mature level that also like TSOs are using that, and big companies like Shell and so on. Yeah, so basically now focusing on PIPSA. Moving to the next slide. PIPSA is a tool that can do both this economic analysis and grid analysis. And within economic analysis, I mean, you don't look just at one snapshot, like not just at one time step, but you can also look into, like, for example, 1 year and try to find out what is the optimal capacity. And yeah, that's the economic part, the investment planning part. And PIPSA can do both, similar to Plexus. It's just open source. It's developed for large-scale optimization and also studies in high spatial resolution. Moving to the next slide. Yeah, and basically what we did in this exercise that we started 6 months ago is that we grabbed the existing RTS GMLC network and we did some capacity expansion, because in the previous event, we just looked at the power flow at really one time step, checked if it's stable. Now we are looking on, okay, if we have a year full of data for renewables and demand, what is the optimal infrastructure we should have. Moving to the next slide. Okay, and basically we looked at 5 different scenarios. So we looked at the RTS base case, yeah? And Clayton was also sending us some data for that. Thanks for that. And then we did some line expansion, only generator expansion. Then we did both generator and line expansion. And at the end, we had also like a net zero case with the RTS network. Moving to the next slide. And basically the whole thing, and that was really a work of the open source community. And basically what we did is we imported the MatPower file, which the RTS was originally in. We imported it in PandaPower, and from PandaPower to Pipesa. And that was like the quickest way, and that's why we did it in that way. But it required some renaming of components and that stuff. When looking at the next slide, basically the challenge was then to add the data. You had this huge network and components, and then you suddenly had to make a 1 year data set out of that. Like that was quite challenging because previously we used it just for one single time step. So adding that took some time, but it was straightforward and worked at the end. At the next step, we added then investment costs. So if we go to the next slide. Yeah, and then that's, for example, the part where we added the time series data. That was the 1 year time series data. Moving to the next slide is actually where we added the investment costs. Exactly, we added capital costs, marginal costs, and some technical details. Then if we move on, we had to add some constraints. So for example, the net zero constraint for the future scenario, or storage constraints. And then at the end, we finally, if we move to the next slide, added the solver part. And yeah, that was it. And now I'm just going to show you a couple of results. If we move on. Yeah, so basically we had this original network and with all the different carriers, and what was remarkable at the first step is that the expansion didn't work with the linearized optimal power flow. So either the supply didn't match the demand, or there was a bottleneck somewhere in the network, so didn't work. Unstable situation here. Moving to the next slide. With the line expansion, everything was fine. So I was relieved, not coding too much. And we could actually discover on the right side a little bottleneck. So there the system thought, okay, investing in this section of the network made sense from the total system perspective. Looking at the next scenario, where we expanded both lines and generators. Click to the next step. Basically, what we then found out in this demonstration is that solar PV was a bit optimized, and that actually replaced CCG. And basically, yeah, I mean, what we didn't include was the unit commitment constraints, so probably wouldn't go in that scale. But yeah, it was interesting that solar was optimized. Moving to the next slide, I think that was the most drastic scenario with the zero emissions, and we had line and generator expansion and in load increase from 1.5 times. And then we thought, like we saw, actually observed that the whole system changed. And yeah, I think that might also happen in some parts of the world nowadays. So moving to the next slide, is actually what we recognized during this task, that whenever you build a model again and again, it takes time to validate it. That one is not even maintained now, so that would also come on top of that. So it's really hard work. Question is why we're doing that. Going to the next slide. Pipes is really just a framework which we use, and I just want to show you that actually we built tools on top of it, and a model uses this framework with the data, and the Pipes team, Pipes community, we work specifically on a European model, transmission system model, where the data is automatically fetched from the best available open data. And then, yeah, building this model is just really like, for one country, it takes just a couple of minutes. And that's really something useful. We also have a sector coupled model, but a model is nothing worth without data. So there's also, in particular, on the supply side, where the Pipes community works a bit. So we are matching power plants in Europe, different databases. So it's like a data fusion task. We also have renewable supply estimations all across the world, and also dynamic line rating constraints that are calculated depending on the weather, and then also a Payomo alternative for the specific energy optimization part. And that's really just the Pipes part, and that was done and is continuously developing over the last 5 years. And we are working on the Earth initiative now, actually on taking all these things on a global level, so that this is accessible in other regions as well. So we started with the Africa model, focusing on power, but that will become the Earth model, which is power and sector coupled model. And then we are also extending and working on not just supply data, but now also on infrastructure data. For example, we can detect from satellites, for example, transmission towers or generators. And that's really useful to model accurately all across the world. And then we have the last part is the demand part. So we have supply, network, and the last part is the demand. And the predictions are not available everywhere. And to plan with the policy partners into the future, you need in all kind of categories good data, and that's where that's why we're working on this task. So moving to the next slide, it's just a clarification. So Pipes to Earth is not a global model. It is, I mean, you can model the whole globe if you like, but you can also just focus on your country. You can focus on Germany and so on. Or if you have even better closed source data available, you can implement it and maybe share it even openly, so that we can sustain that and reuse that, and not doing a ton of duplicated work that we see all around the world. And then moving to the next slide, that's where I'm ending. Basically, our vision is there to create together the most compelling open data and open source planning tools, specifically for this invest in the dispatch planning purpose, to accelerate sustainable energy transition and challenge then the black box modeling standard that we have often today. Yeah, and I really enjoyed the whole exercise. That was quite fun. And I think I'm handing now over to the next speaker. Yeah, Roman. Thank you.
Hello, everyone. Welcome to my part of the presentation about Panda Power. Next slide, please. Here you can see the links for the official website and the GitHub repository of PendaPower and the documentation. You can also see the organizations behind the PendaPower repository, which is Fraunhofer IEE, the Institute for Energy Economics and Energy Systems, and the University of Kassel. And in the next slides, you can see the case study that we performed with PendaPower for this exercise. We see the image that represents the power system and the different zones. The red lines represent the connections between the different zones. We had to adjust the power system in order to have AC feasible power flow. We converted the conventional generation from PQ node to PV node in order to have proper reactive power management. Then we also are using distributed slack that is covered by the conventional generation. And also we added the transformer type changer controller from PendaPower. And in the next slide, here we see the initial scenario for the power system. We see the representation for the load and for the conventional generation and the renewable generation. And the conventional generation is used to cover the gap between the load and the renewable generation. We do not perform a correct unit commitment study or unit commitment calculation, but we use the installed power of the conventional generation to scale it up and down with the distributed slack approach. And then at the next step, we perform redispatch for conventional generation and renewable generation in order to limit the line loading. Please, next slide. We see in the initial calculation that lines are overloaded, that we use the distributed slack approach for conventional generation, and this results in lines being overloaded during many of the time steps. Next slide, please. We set up the AC OBF with linear programming problem formulation. We are assigning positive costs for conventional generation and negative costs for renewable generation. The purpose of this assumption is to maximize renewable generation and to prioritize a redispatch of conventional generation. And for the time steps that do not have a solution, we enabled a repeated calculation for the updated assumption that also load shedding is allowed. And this was necessary for one time step in the case study. And on the left, you see the mathematical formulation of the linear programming problem. The DF stands for the distribution factors. And the limits of the problem describe the requirements that lines are not loaded above the maximum current rating. And also we have a limit for the power change of every pass. And next slide, please. We see that after performing the time series simulation for 1 year, we could achieve that all lines are not overloaded anymore. And in comparison to the red line, which was the initial simulation, you can see that the blue line maintains line loading below 100%. Next slide, please. And here we see what was necessary to achieve that result. We see that the redispatch of conventional generation was necessary, but in comparison to the initial generation, the change was not that high, the change that was required in absolute values. And the reason for that was that the balancing was already performed with the distributed select approach, and the redispatch simply redistributes the conventional generation across the power system in order to limit the line loading. And with that approach, we did not have to apply power curtailment to renewable generation. Next slide, please. The conclusions from the case study can be summarized as following. The challenges for the AC linear programming OPF are the performance. We need to repeat the power flow calculation and the AC OPF calculation multiple times per time step until the convergence of the solution occurs. And also sometimes we can observe oscillation of the solution where the optimization is jumping between one solution and the second solution many times. In this case, we have to stop the optimization and accept one of those two solutions. But the advantages are that the solution of the APF is AC feasible. The advantage is that the convergence is more likely in comparison to some other OPF formulations. And it is possible to separate the overall problem into the power flow calculation problem and the OPF problem, and also to include the outer loop power flow control functionality, for example, transformer type changer, and this allows for a faster, a shorter way towards the solution of the problem in terms of the implementation. And further work that can be enabled by this approach is security constrained ACOPF. We could also consider preventive and curative measures, and the formulation of linear programming would also allow us to include reserves due to thermal inertia. Thank you for your attention.
Hello. So I'm Nicolas Aumont. I'm going to present possible metrics and the application to the GLMC RTS model, which is the same dataset as the one used by Roman with Panda Power. Next slide, please. So just a few words about Possible. Possible is an open source framework written in Java and dedicated to power grid analysis and simulation. It was created 10 years ago through a EU-funded collaborative R&D project, and it now has a community of 70 users. It allows to perform power flows, optimal power flows, security analysis, and dynamic simulation, among other computations. It supports many formats: SIM-CGMES, UCT, MATPower, PSSE, and so as it was asked in the discussion, it supports node breaker models. So you can perform grid topology operations You can do extraction of subnet networks, merging of several grid models. It has a Python binding, so it makes it friendly to non-Java developers. And you can use the Groovy script to do some fine-tuning. It has advanced features like visualization tools, especially if you want to visualize very large substations in node breaker models. Next slide, please. Metrics is a computation module that is integrated into Possible, which is used to assess and optimize preventive and curative remedial actions to satisfy network constraints on a high number of variants or of points. In metrics, you will find a network model. You will find load and non-dispatchable generation time series, and then you will find the actions that are allowed to address a constraint violation that are redispatching, curtailment, and loss of load, as well as topological remedial actions. And of course, a list of contingencies that you have that the optimizer has to cover to ensure the safety of the grid. Next slide, please. So there are three computation modes. The simplest one is a simple DC security analysis. It's a simple DC power flow, very fast one. So as input, you've got the network model, the base case topology, the contingencies, and the load and generation time series with generations that must match demand. Else, there is a slack node. There is no slack node. The adjustments are done with marginal costs of generation units in a kind of small base case OPF. As a result, you will have flows at each element and the maximum flow violation, both in the base case and in the contingency case. Then there are two security constraint DC OPF, one that does only topological action and no redispatching. And then the objective is to minimize the maximum flow violation. And so in addition to the standard, to the DC security analysis mode, you have to give all the available topological remedial actions, both preventive, so before the contingency occurred, and curative after the contingency occurred. So as a result, you will have the selected preventive actions, the selective curative actions for each contingency, and the remaining violations. And the last mode is some standard SC-DC OPF with redispatching, in which you try to minimize the global cost of redispatching while satisfying the maximum flow constraints. So the inputs are similar to the previous mode, except that you must give the redispatching costs. And as a result, you will have the same result as before. In addition, you will have the adjustment of generation and consumption that is redispatch, curtailment, and loss of load. So it's a bit cut, but at the bottom of this slide, you will find more information about all the features of possible metrics. And especially there is a tutorial that go through a 6-node grid and explain all these features one by one. There is the tutorial is available if you want to go through it and do it, install the tool and go through it. Or there is also a small presentation and a small video if you want to have further information. We could also organize another G-PST webinar for this one. We will now focus on a reduced set of features that are in line with the model that we studied today. Next slide, please. So for the RTS GMLC model, what did we do? So we loaded the network from the mat power format, and then we mapped the non-dispatchable generation and the load time series all over the year, 1 year on each node. And we also mapped the dispatchable generation initial set point. So we start from a unit commitment because somehow, as you will see, the marginal, the cost of redispatching is rather simple. There is only an upward cost and a downward cost for each unit. Then we added all the contingencies. That is 120 elements. So we want to have a solution that is robust to all these contingencies. And for the remedial action, we only allow preventive redispatch, which is a situation that occurs in many countries where only preventive redispatch is allowed. Then we finally evaluated the value of an interzone transmission line, interregional transmission line, by comparison of the cases with and without this line, so that we can see if by adding the line, or you have more redispatching, or if by removing it you have, if you by adding the line you have less redispatching, or if by removing it you have more redispatching. So, and then the KPIs, the key performance indicators we looked at were the flows on the 4 interzone transmission lines that are in bold on the map, the localization of their threats, that is the contingency that is leading to the largest flow on a given line, and then we assessed the cost of redispatch and curtailment. So the data is given below. It was provided by Clayton, Barrows, and the NREL. Next slide, please. So the base case without contingencies is quite simple. Just to illustrate, to have a starting point, you see that there are almost no constraints, no constraint violation, which is quite usual. There are a few ones, so that if you try to do some redispatch, you will have a small effect on a few time steps, but not so much. So it was just to show the difference with the next slide. Next slide, please. Where we did the security analysis with all the constraints. And in this case, we can see that on the purple line, there are a few time steps where there is a significant overflow. And when we do the optimized power flow, allowing preventive redispatch, we see that we solve this issue, we address the issue, and that the flows are within the limit, which you can see on the graphic on the bottom. So the time performance is quite good. It's less than 1 minute for all the time steps. So each of them is solved independently, but very fast, one after the other. And so that what allows to perform the OPF in less than 1 minute over all the year. Next slide, please. So just to illustrate also what you can quickly have with the output is that for the green line, you see that most of the time the contingency that creates the maximum flow is the same. It's the line 318 to 223, and it's not very well indicated, but as you can imagine, it's the purple line, and it's a pair. So if you look at the thread for the other line, it's for the purple line, you're going to find that it's the contingency on the green line. Next slide, please. I think it's still the same slide. So next slide. Okay. So then a smaller result on the redispatch. So you can see that the redispatch cost per hour is around, it's between $0 and $8,000. And you see that there are 3 regimes in which in which an additional load, an additional megawatt hour of demand is increasing the congestion, which is somehow expected. So either there is no congestion, this is what we see when the hourly redispatching cost is 0, then there is a zone where the additional congestion cost of 1 additional megawatt hour of demand is around $0.1, and another one where it's around $0.5. Next slide, please. Next slide. And then the last thing I said we would look at is the value of a transmission line. So if you take the purple line and remove it, and then compare the redispatching cost in the two situations, you can plot the redispatching cost over all the year. And what you see is that this line brings some value in reducing the congestion all the year long. And if you sum this all over the year, you can have an idea of the cost, the costs that are saved thanks to this line over 1 year. Next slide, please. And it's around $4 million a year. So it's a cost that allows to build a small line, but that's not a very large cost. And the main reason is that usually when you build a line, you need that it avoids some load shedding. It's not the case here. That is, even without the line, you don't have load shedding. But that the kind of it illustrates the kind of study you can do with this tool, which is really dedicated to evaluating whether you have to perform an investment on a given line. So the redispatch model is rather simple, but the grid model is rather complete with the preventive and the curative remedial action, topological ones. And you can have the HVDC, PSTs, and so then you can really simulate what's really needed to compute the value of a new investment or a new reinforcement. Next slide, please. So yeah, just to conclude, so possible metrics is a security constraint DC optimal power flow. It handles both preventive and curative remedial action, redispatching, HVDC, HVDC set point adjustment, and topological action, and also phase shifter are included in the optimization. And it is built for outstanding performance on sequential simulation, even if each timestamp is served independently. So we have illustrated this on the RTS GMLC model. We have seen the maximum threat a line is subject to. We have seen that we can compute the cost of redispatch and compute the value of a line by comparison of the redispatching cost with and without this line. You will find more information online, an installation guide, and a tutorial that is very useful to start with on a 6-node grid, where you can really understand all the concepts about preventive, curative, remedial action, topological action, redispatching, and that really we will be happy to help you on board thanks to this tutorial. Thanks for listening, and I give the floor to Clayton. And you will not hear any more next slides because Clayton is going to.
Oh, no, I will keep having Emily advance. So go ahead, Emily. Thank you, Nicola. So I'll talk a little bit about some of the tools that we've enabled through an initiative at NREL. They're all based in the Julia programming language and ecosystem. And so starting with Powersystems.jl, which is the data handling package and creates a pretty rigorous data model for transmission level power systems and allows you to store the data for quasi-static and load flow cases and optimization based modeling like production cost modeling, as well as the dynamic parameters for many of the elements in the system. So you can, it's one of the few data models that exist that allows you to express both the dynamic data for transient analysis, as well as for the quasi-static and stable or steady state optimization type modeling. So we can, and in addition, we can store the time series for a large, for really any parameter. And we enable parsing from several of the standard data formats like mappower.m files, raw files, DYR files, and then we have some custom capabilities from CSV files and things like that. There are a number of other capabilities enabled by Powersystems.jl. If you're interested, check it out. But it is the foundational layer for which we'll do some of the modeling in PowerSimulations.jl. Go to the next slide, please. But in this example, we are using a kind of a new package that I put together that's still in development, but it allows us to take the data that's written from PIPESA in the .nc files that PIPESA writes and instantiate a power system representation so that we can use the modeling packages in the Julia ecosystem to analyze the system. So this will take the scenarios that Max created with PIPESA and create a system. And there are definitely areas where this is incomplete, but it does a decent job of translating the data and all the time series that comes out of it. And I'll show some examples of that in a minute. Next slide, please. And then we'll use PowerSimulations.jl to do some optimization-based modeling for these examples. Power Simulations is really built around formulating optimization problems and sequences of optimization problems, and allowing the user to specify how the data flows in between the problems and inform subsequent problems. So we can do things like unit commitment, economic dispatch, and then things like production cost modeling, where you solve many unit commitment steps and inform subsequent problems with or subsequent steps with the results of previous steps. We have co-optimization of ancillary services and can do a number of different formulations for power flow, including a number of AC formulations, which result in nonlinear programs, so they're often difficult to solve. Next slide. One of the real benefits of power simulations is that it provides a lot of flexibility around defining your sequence of simulations. And so we have this concept of decision models where we're really looking at forecasted information, and we're informing decisions about how the system might operate under those expectations of what's going to happen in the future. And then we have this concept of an emulation model, which in principle is really emulating how that system is responding. And so we can use those two concepts to simulate how a grid might be scheduled and operated and respond to different types of perturbations, like disaster scenarios or forecast errors, or a number of things like that. And so we have a lot of flexibility in defining this, using these two model specifications to define a simulation specification, where each of the problems represented by this sort of Gantt chart looking thing is informed by the results of previous problems, and allows us to represent the schedule, the forecasted schedule, the actual schedule, and then the system response, or the emulated system response at each time period throughout a horizon. And so next slide. In this example, I've simply taken the results from PIPESA and formulated a day ahead sequence. So there's only one stage. There's no economic dispatch with different forecast information or anything like that. It's simply looking at a day ahead market clearing type process using the infrastructure build out that PIPESA has identified as optimal. And so to do that, I've assembled a model with a single decision model, or assembled a simulation with a single decision model. You can see on the left, there's a UC, and that decision model is the single model in the system. And I've defined in that model how each device type should be represented, whether we're going to be doing unit commitment with the thermal generators, and then being able to dispatch and curtail renewable generators, and how the loads and the lines and transformers and all the other resources in the system are represented. In this example, I've simulated 364 steps. We have an 8760, so we have 8,760 hours of time series data. which if we're doing a day ahead unit commitment and solving steps where there are 48 hours in each step, that allows me to simulate 364 days. And so this sequence will solve 48-hour problems, and each time that problem is solved, it'll step forward 24 hours and inform the initial conditions of each problem with the results of previous problems. So we can respect the constraints of minimum on and off times and ramp rate constraints with the results of previous problems. And so this is the type of output as you assemble the problem you get from Powersimulations.jl. And then once you build the problem or compile it into something that you can hand over to the solvers, you get the output from the right, where it summarizes how long each step took and the compilation step takes and things like that. Next slide, please. So then we have another package, auxiliary package called Powergraphics.jl, which allows us to explore some of create graphical representations of some of the results of power simulations. And here are some basic examples of what those what types of plots can be created. And this is currently in a lot more development. So there's a bunch of new plots that are being enabled pretty regularly. Next slide, please. Some examples from this simulation. So here's sort of the first or just a sample set of 4 days of 4 of the scenarios of the results produced by PIPSA. And we can see that the operational profile from the different scenarios is quite different. So PIPSA produced very different resource mix on these different networks. In the bottom right, you can see the case where the load is quite a bit larger than the other cases, and the parameters that are produced by PIPSA are pretty. They're pretty. In this case, they're a little bit simplified. So some of the ramp rates and min stable levels for unit commitment and things like that are a little bit more flexible than we might see in more realistic data sets. But nonetheless, you can see that the operational differences from these scenarios are quite stark, and and it's been useful to pass them through the power simulations and power graphics to see the differences. Next slide, please. Similarly, when we just look at the annual generations, we did simulate all 52 weeks and summarize the total energy generated by different fuel types. We see quite a different set of results here. Next slide. So all the results are exposed in data frames, and that's really, I think, one of the powers of these types of modeling capabilities that exist within a complete language and that's suitable for data analytics. This is a plot I just made this morning based on the data frames that are available in the results of prices. And so I just made a price duration curve, which isn't all that interesting because of the simplicity of this network. But the reality is that exposing all of the results for all of the parameters and variables and dual values and auxiliary variables that exist in the models, it allows the user to do some fairly advanced data analytics on the results of these problems, all within the ecosystem that's available from Julia. And of course, all of this is exported to CSV files or more easily accessible formats. So you could read it into Python as well and do other things. And so I think it's all very accessible and provides a lot of value from the data analytics standpoint. Next slide. I'm not sure why there's animation here, but some other things, this isn't necessarily representing the data coming from PIPSA, but some other things we've done with the RTS network with power simulations. So we've done a lot of benchmarking to make sure that the results we are getting are equivalent to some other tools, most notably with the commercial production cost modeling software Plexus. We've done a bunch of benchmarking with the RTS as well as a number of other networks. And in these examples, we've been able to get to the level of numerical precision that's consistent with the combination of the solvers and the computational representation of the data. So we're quite comfortable with the validity of the formulations and the data handling in power simulations. And we're also quite happy with the performance. We're getting between about 2 to 7 times acceleration over the same model in Plexus, and that depends a lot on a number of things. So I won't present any rigorous computational performance comparisons. Next slide. One of the other things that we can do, and this also appears to have an animation. I think there should be a, yeah, I don't know why it's there. One of the other things that we can do is we can start to analyze some more advanced topics like AGC, or automatic generation control, and reserve deployment with these systems. And so we've done a fair bit of this with the RTS, where we take the co-optimized reserves or ancillary service scheduling and evaluate how in a mathematical programming problem, evaluate how the reserves, the frequency regulation reserves would be deployed to maintain system balance. And so these types of analysis allow, in being able to sequence this problem within a full simulation allows us to analyze some more advanced topics like the value of reserves against different types of forecast errors and things like that. Next slide. Yeah, and finally, all of both power systems and power simulations fit within a larger ecosystem. I talked a little bit about Powergraphics, but there's also another package that I haven't talked about called Power Simulations Dynamics. And so you can, where we can do small signal stability as well as full transient simulations and address some of the issues of low inertia systems and represent very short time scale issues, including some of the phenomena associated with electromagnetic transients. So, it becomes a quite powerful ecosystem that allows you to address a lot of these things in a scalable platform across a number of different timescales, including, long duration scheduling all the way down to some of the electromagnetic transients. And that is the conclusion of the power simulations section. And we can talk a little bit about some of the outcomes that and the lessons we've learned throughout this process. So this has been a process where we, as a team, the 5 or 6 of us as a team have gathered, go to the next slide, fairly regularly over the last 6 months or so. And throughout the effort of assembling the first event where we were focused on the power flow calculations and the common problem and sort of doing some benchmarking and then working on this common workflow, I think one of the principal takeaways is that there's a lot of value in being able to exchange data between these tools. And so that has raised a question of, is there a need for better data specifications and formats? And I think that, the common answer for this is, well, we have one. We have a very complete one with the Common Information Model, or SIM. But one thing that we recognize is that that's very designed for operational data exchange and maybe isn't always suitable or practical for some of the planning type studies that we've talked about here. On the other hand, some of the model specific formats like MapPower or the PSC raw files are fairly well specified, but they're incomplete. They don't always contain time series information, and they have a lot of modeling assumptions baked into the data format. So they're sometimes challenging to use as well. And so is there a need for something in between? And we noted the other day when we were discussing this that RTS GMLC maybe starts to represent what could be in between, where we have a data set in a format, it's maybe not well specified, that that is relatively complete for these types of studies. Certainly could be extended in a number of ways, but the popularity of it and the ease with which people have read that data and started doing analysis with it maybe suggests there would be value in working on a specification that is more designed for this type of work. Next slide. Some of the outcomes that we've seen here, I think a lot of it is around integration. There's the pipes to the Powersystems.jl package. We also made a number of data transitions, pass data back and forth by using Powersystems.jl and then using some of the capabilities that exist in PowerModels.jl and an integration between those two packages to be able to export map power files. Everyone on this panel has made extended some capabilities to parse, read, and represent the RTS GMLC formats and network. I think in most cases that's a data set generalized beyond just the RTS GMLC network. So like if the data is in more or less that format, one could read a different network. And then there's been a nice improvement to the connection between Panda Power and pipes to enable data translations. Next slide. I think that is it, and we can address some questions. I'll hand it to Juha to moderate.
All right, hello. So let's start with a question from audience. Sofia Sipanic asked about the use of transient constraints in capacity expansion. Max already indicated that PIPSA community would be interested in developing that capability, but I would kind of maybe extend that question and ask then what aspects of transients would be interesting in capacity planning? What would you see to take in if you would have the freedom to do so? And if your models already have some of that, I would be of course interested to hear as well. So we can do a roundtable. Maybe if Max, you want to first add something.
I mean, basically the transient part is not there yet, and I think it could be interesting looking into future scenarios and you know, analyzing then the stability of these future scenarios. I mean, it's certainly valuable. I think it could be a module, and probably there are tools already out there doing that quite well. So just linking them together practically could be really interesting. I mean, that's my view, but probably Clayton, you have more insights to that area.
I'm definitely interested in hearing from Roman and Benoît and Nicola, but I'll state my view on this. I think it is really interesting. I think there's definitely a set of emerging questions about if we displace a lot of synchronous generation and even the transitions between steady state set points could become stability concerns and things like that. So it's not clear to me how to endogenously include stability constraints in a capacity expansion model yet. I think there is some work in this area that I think is really interesting, but I think there's a lot of opportunity to just address some of the concerns with coordinated workflows. And I think the type of workflow that we explored here is a start. So capacity expansion modeling, and then optimal scheduling, AC power flow to instantiate to establish a AC feasible set point, and then understanding the stability of those set points to various perturbations. And so there's a lot of value in being able to, in data completeness, data translations, model integration, to enable that type of workflow. And you could certainly see a future where that all gets integrated into an outer loop optimization, where you are evaluating the stability and feasibility of different expansion, or even for that matter, unit commitment scenarios. But I think there's still a lot of work to get there. So. Roman, Nicola, Benoît, anything you'd like to add?
Not much to add. There is no unit commitment in Possible yet. It's more a grid tool. But indeed, particularly from my personal experience, what I see is that people do include already inertia constraints in their model. I mean, if you take the Irish system, basically, if you say you do not want more than 70% of wind power, it means that you have an inertia constraint in your unit commitment. So it's a cheap way to do it. It's true that if you want to go further and to do the dimensioning of the inertia constraint together with the planning, it's complex. But if you already have the inertia limit, you can at least include it as a kind of ancillary service, like if it was a reserve in your model.
I'll just be short, and I will say that in PentaPower, we consider transient calculations out of scope.
All right. Then Clayton, you have a question that you could maybe answer in the chat side, but I could then ask the panel. Meanwhile, that Max was referring to the issue of maintaining model instances, and so maybe we could do a round of what do you find especially difficult, and what could help you to do better in maintaining models once you've built a model that works.
Like, just from my perspective, is keeping people for long term on a model, because you have maintainer, like you don't become one from one day to another day. Having people having opportunities even for open source models to work long term on it, I think that's really important. And here, I mean, it's great with Possible, for example, working with RTE there together. Such opportunities, I think that's super helpful to keep things alive, and also to push the boundaries of what's possible.
Nicolas?
Yeah, on my side, which is more operational, I'd say that agreeing on the way to describe the grid and the way to describe the actions and the models is very important, because sometimes even if you have defined a conceptual data model, people don't use it in the same way, and so then in the end, when you get the data, you don't know which behavior is expected, so you have to iterate quite a lot to understand. So there has been quite a lot of work done with the SimCGMES, but I think we are not at the end of the road, and that we still have to work quite a lot to be able to build quickly pan-European models with data that comes with several tens of TSOs.
Is it also then a question of defining better the data structures, and what do you mean by things in your data structure?
Okay, let's say that sometimes people, let's say that someone want to say that you should not use a phase shifter regulation somewhere, and then instead of deactivating it, just put a huge deadband. Well, the result is the same, but somehow using a very large deadband is not supported by most of the tools, which expect the deadband to be reasonable. So that's more tricky things like that, so that makes it difficult to converge. So the data model, they send something that satisfies the data model, but that's hard it's hard to handle all the peculiarities of all the TSOs if they use the model in a different way.
I have, from my own experience, I feel that it's important that when we define models and parameters for models, we don't immediately expect something to happen when you define a parameter. I think there should be a separate switch that actually activate activates things, so you can kind of use that to make things happen and not happen. Makes it more clear. It's more work, but then becomes more clear what do you mean by your numbers.
Yeah, indeed. Takes time.
Roman.
I could identify two aspects that I think are challenging. One of them would be the definition and the maintenance of converters between one format of data to a different format of data. And then a different aspect would be that for certain analysis kinds, or for certain grid planning exercises, different detail grade of the model are important, and if the format of the model, or the model itself, in my experience, should then be adjusted in order to consider those maybe additional details for a particular power expansion exercise. For instance, one such example could be modeling of every current carrying system separately and not as part of the one single line. So to say that we have, let's say, 4 lines between 2 buses, and they all belong to one overhead line. And that imposes additional constraints on the power system planning.
All right, Clayton, any thoughts on model maintenance?
I mean, I think that a lot of what we've has been described by the panelists is kind of like a model limited choice or a data provenance issue, where the data has been assembled to suit a specific model and then been adopted by a different model, and there's difficulties in that translation, and there's assumptions that need to be made in that translation, and the availability of some of that data, it limits what you can do with the modeling. And I think that's becoming important, more and more important, as we kind of need to explore new modeling solutions to address some of the emerging issues of the power system. And so I think it just harkens back to the need to create a very rigorous data specification and then enable translations to the best that we can in and out of that specification. So I think that's the main, and honestly, the hardest thing has been data specifications and parsing for maintaining these types of models, parsing the data files and making sure that you're representing the data properly and doing any of those translations. And that's been the most challenging thing. Everything else is quite a bit more simple than dealing with other people's data formats, I guess, is the hardest part.
All right, there was a question about including stochastics and robot constraints in your scenarios. You could maybe answer in the chat from Jose Nicolas Melchor Gutierrez, but I will formulate also the question from Eza that is similar here, that that we could take here on the panel, so that about capturing uncertainties in power system models. So what kind of capabilities you have or plan to have or would like to have in terms of having robust or stochastics in the power system modeling analysis? And maybe yeah, Clayton, go ahead.
I'll just be very brief and state that we have a number of extensions. I mean, power simulations is very modular and extensible. So we have a number of extensions, mostly are not publicly available yet, where we've explored stochastic optimization techniques. But in general, in our core supported packages, we are representing uncertainty by explicitly representing forecasts and the recourse on the decisions made against those forecasts. So enabling these types of sequences where you may be optimizing 48 hours, but then you re-optimize that with a new forecast, hour ahead forecast or something like that in the process of scheduling these systems. But we are also looking at robust and stochastic programming extensions, but they're not part of the core packages yet.
Anyone else wants to add?
I can add that the robust / probabilistic type of power system expansion planning could be achieved by considering not one scenario, but a multitude of different scenarios for the generation and for the consumption as inputs, and then evaluating the multitude of the results for each of those scenarios in terms of the power system model that is achieved.
Oh, yeah. Somehow, I think the question is right, and the fact that we have renewable energy, variable renewable energy, changed the way to do the network expansion planning and the dimensioning. Before, it was most of the time on peak load, which was quite easy to identify. But now, given all the correlation between the load and the renewable generation, you really have to study annual time series and to look at all the time steps one by one. So this is what was done in possible metrics, whereas the previous version of the tool would rely on a more probabilistic framework where you just draw contingencies and outages of power plants. So that's how we took this into consideration. And of course, to compute the value of a line, you've got to compute it over several years, climatic years, to get an idea of its value. So, and then for the robustness, if you think to robustness beyond n-1, but for example, robustness to future scenarios. So for example, high growth, low growth, base case, and or various penetration of renewable energies in the future. So you want something that is a trajectory up to 20 years, and then you want the first step, the 5 first years, to be robust to the fact that you don't know what will be the scenarios after that. Then you have frameworks that allows to do it, and in other tools that we have, we start to have them, but in the end, you have to remember that you will have to explain the results to real people. And when you have a problem where you solve a trajectory over 20 years, and then that you have climatic scenarios, and then scenarios for the growth or for the prices, that you combine all of them together and that you want robustness, then in the end, you've got to be able to make sure that the people you will present the result will understand. So usually what we do is we do various trajectories one by one, and we show the results one by one, but we do not try to have a first step that is common to all the trajectories.
Max, you want to add, or should we take that? Probably the last question, or getting close there. I would just say that if you're interested, I've been involved in a model called SpineOpt that has a very flexible stochastic and temporal structure. So you could build both generation planning and unit commitment economic dispatch models that can have the stochastic structure of your choice. But there was a question from Abdelrahman about solvers. What solvers you require for unit commitment and economic dispatch problems? And Clayton, maybe you start, as you indicated.
Yeah, I mean, so everything that I presented is built upon the JUMP package, jump.jl, which is Julia for mathematical programming. And so any solver Some solvers are suitable for certain types of problems, and so there's some compatibility. But any solver where there's a jump interface is one that we can, in principle, support. So all the results I presented today were obtained with the HISE solver, which is an open source solver. But for very large problems, I tend to use some commercial solvers like Gurobi or Express. And but if I can on smaller problems, I tend to prefer to use the open source solvers like HISE or CDC.
Yes, in possible metrics, the solver uses one that has been open sourced and that is quite specific to possible, which is called Sirius, and it's on the roadmap to have a Google OR interface that will allow to call any commercial solver. But somehow the current solver is really tuned for possible metrics and is very efficient for the problems we have. And so it also allows to have a full open source stack that is efficient.
All right. Just as a closing question, are all of the aspects of your tools open source, or is there still something closed in there? In what you were presenting today?
Everything in the work that I presented is open source.
Yeah, same thing for possible metrics.
Same for PipeSer.
The part that I presented today is not open source. The AC formulation of LP-OPF is not open source.
All right, thank you. Actually, we still got one more question coming from the audience about the data and preparing the data for model. It's noting that is one of the most time-consuming tasks, and it certainly is. So that do you have any ideas to how to streamline the process of getting data to the models, other than the things we already discussed about getting data from other models? But when you have a raw data sources, how do you get them faster, easier into your system?
Like from our side, we have really nice experience with workflow management tools, and Juha, I know that you also work on one. So that really helps the whole process. And what we actually usually do is creating workflows from primary databases, Copernicus, NASA, or something like that. And then we create these workflows into the model. And with that, everything is transparent. Like, that's great. The whole workflow to get and modify the data is transparent. You can reproduce it. And then on top, if you want to speed up some things, you can also provide model-ready data, be it hosted somewhere or something like that. And yeah, I mean, that whole process with workflow management tools, as you might know as well, Juha, is super cool. And I think it really enables accessing data from everywhere, from primary databases, and not just modified data, which is probably outdated quite quickly.
Any other thoughts?
I'll add that I think that it starts with strong data specifications, which allow you to build validation checks and tests on the data that you're ingesting, and then in a programmatic environment, it allows you to build these reproducible workflows, and then you can manage them with the workflow managers. That's really helpful. And so I think that all of this lends itself to having access to programmatic tools, and then building each step of the process. And it's certainly not easy. And so I think that's a thing that each of the representatives here have grappled with and tried to help address.
Thank you, everybody, for joining. I think it was a great pleasure to see all the presentations and have a lively discussion. Emily, do you have anything more to add?
I do not. Thank you, everyone. And as a reminder, we do have a survey that will launch when your session closes, and we'd really appreciate your feedback. We will send you an email after the event probably next week with a recording of the presentation, a link to slides, and a link to all the resources shared. Thanks, everyone. Have a good day.